In this video, we'll work through every question from the Junior Kangaroo from 2023. That's one of the follow-on rounds to the Junior Maths Challenge, aimed at students aged 11 to 13. You can also practice all of these questions and more in a free course at the Mathsaurus website that I'll link below. That course also has hints to help you get started with each question, and there are no ads or distractions there like there are here on YouTube. But if you'd rather stay here, you're very welcome to, of course. I'll read out the question before each solution so you can pause the video and have a go at each question before watching the solution. So let's get started now. Which single digit should be placed in all three of the boxes shown to give the correct calculation? You could get this by thinking about the rough size of them or just working them out. You could speed it up slightly by thinking about the last digits maybe. You know, if this was 33 times 3, we just need to think about the last digit. 3 times 3 would be 9, so that definitely wouldn't work. But 4 times 4 is 16, that would end in a 6, so that works. 5 times 5 is 25. That wouldn't work. 6 times 6 is 36. That could work. 8 times 8 is 64. That won't work because we need it to end in a 6 here. So it's either 44 times 4 or 66 times 6. You can see 66 times 6 is going to be bigger than 60 times 6, bigger than 360, so that's clearly not the right answer. And 44 times 4, you can double check, really is 176. And so it's 44 times 4, and the answer is B, 4. The sum of the ages of 3 children, Ava, Bob and Carlo, is 31. What will the sum of their ages be in 3 years' time? Well, in 3 years' time, each of them will be 3 years older, so we don't need to know their individual ages. We know they're each going to contribute an extra 3 years to the total. So the total in 3 years' time is going to be 31 plus 3 plus 3 plus 3, or 31 plus 3 times 3, and that's 40. And so the answer here is going to be D, 40. Nico is learning to drive. He knows how to turn right, but has not yet learned how to turn left. What is the smallest number of right turns he could make to travel from P to Q, moving first in the directions shown? So we start at P here. We could make a right turn along here, and then we'll have to make a right turn here because we can't turn left. Now I've got a choice here. I could turn right here, or I could keep going and turn right down here. If I go down here, the only options that involve right turns involve doing loops again. I can never exit to the left. So really it makes a lot more sense to go down here and then to go along here, and then we're going to go up to Q. Again, you know, if I turned right here instead, the only option would take me back a less efficient way to somewhere I've already been. So overall, how many right turns is that? 1 here, 2 here, 3 here, and 4 here. And so the answer must be B, 4. A doctor told Mikhail to take a pill every 75 minutes. He took his first pill at 11:05. At what time did he take his fourth pill? Well, the fourth pill will be 3 pills later. So what we want to do here is 11:05 plus 3 lots of 75 minutes. And we've just got to be careful about the conversion of minutes and hours here, not to get things mixed up. 3 times 75 is 225 minutes, or it's 3 lots of 1 hour and 15 minutes. Either way, we get to that being 3 hours 45 minutes later than 11:05. The answers are given in 24-hour clocks here, so we can just add these together then, and we get 2:50 p.m, and that must be the answer, so it's C, 14:50. When she drew 2 intersecting circles as shown, Tatiana divided the space inside the circles into 3 regions. When drawing 2 intersecting squares, what is the largest number of regions inside one or both of the squares that Tatiana could create? If you start playing around with this, you'll realise we can do a lot more than with the circles here. We want to try to increase the number of times the squares overlap each other, and the number of times they intersect basically, because that will, each time they intersect, will give us an extra region. What we want to do here is, if you rotate one of the squares, you can get lots of intersections by putting them on top of each other like this, and then we can count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 regions here, and so the answer here is E9, and we can't get any more than that. It's quite nice when the largest answer is the correct answer here, because you don't really have to think further about why that's the case. The answer must be what you've given there. The integer 36 is divisible by its units digit. The integer 38 is not. How many integers between 20 and 30 are divisible by their units digit? Well, let's just go through and check. 20 is not divisible by 0. 21, yes, that's divisible by 1. 22 is divisible by 2, it's even. 23 is not divisible by 3. 24 is divisible by 4. 25 is divisible by 5. 26 is not divisible by 6. 27 is not divisible by 7. 28 is not divisible by 8. 29 is not divisible by 9, and again 30 not divisible by 0. So we've got 1, 2, 3, 4, and the answer here is C, 4. What is the largest number of T-shaped pieces as shown that can be placed on the 4x5 grid in the diagram without any overlap of the pieces? Well, each of these T-shapes is 4 squares in it, and the grid is 5 by 4. So we definitely can't do more than definitely can't do more than 5. We can try and see if we can get 4 or 5 in. If we start playing around with this, you'll see actually there are quite a lot of ways that you can get 4 in here. So I could do 2 there, I could do a third one here, and I could do a fourth one here. I've actually, so there's 1, 2, 3, and 4, and I've got 4 spaces spare, but actually there's no way of arranging these to get the 5th one in. If you play around with this enough, you'll probably convince yourself that that's true. If you wanted to do something more formal here, you could do a colouring proof, which says, imagine it was actually like a chessboard like this, and the squares go black, white, black, white, black, white. Could we cover this with 5 T-shapes? Well, a T-shape either has to have 3 black squares and 1 white, or 3 white and 1 black. And so if there were 5 of these, you'd either have to have 5 of this type and 0 of this type. Clearly that's not going to work because almost all the tiles were going to be black here. So they're going to have to be relatively balanced. You can, if you think about it, the only one that might be sensible is to have either 3 and 2, 3 of these and 2 of these, or 2 of these and 3 of these, to try to keep the numbers reasonably balanced. But you see, if you had, let's say you have 3 of these and 2 of these, that would give you 11 black squares in total, because there's 3 in this one and 1 in here, and you would have 3 plus 6, which is 9 white squares. But the picture here has 10 white squares and 10 black squares to be covered, so that's not going to work. And you can check any other combination of that also isn't going to give you a balanced number of black and white squares. So that's how you'd really formally prove it. For the purpose of answering a maths challenge, I would probably be happy just to convince yourself that the answer here is 4, and to move on, and to come back and think about this interesting proof once you're finished. Peter the penguin likes catching fish. On Monday, he realised that if he had caught 3 times as many fish as he actually did, he would have had 24 more fish. How many fish did Peter catch? You could try the options out here, I suppose, but really this is a good use of algebra to speed things up. So let's see, if he had caught 3 times as many fish as he actually did, so let's call x the number of fish he actually caught. So 3 times x would be 3 times as many as that. That would be 24 more than he actually caught, so that would be x plus 24. A nice easy equation for us to solve here. Subtract x from each side and get 2x equals 24, and divide by 2, and we've got x equals 12 there as the answer, so it's A12. Maria has drawn some shapes on identical square pieces of paper as shown. Each line she has drawn is parallel to an edge of her paper. How many of her shapes have the same perimeter as the sheet of paper itself? There's quite a well-known sort of type of question here that underlies what we're doing here, which is that when you take a rectangle, if you kind of cut off a corner like this and you make these nice straight lines that are all perpendicular to the edges, then the shape that I end up with here has the same perimeter as the original rectangle, because it's like I've moved this side to this side and I've moved this bit to here, but I haven't changed the overall length of the perimeter. And that's the idea we'll use here. So if we look at this first one, that's exactly the sort of thing we've done here. This is the same as this is the same as this, so this one does have the same length as the original square. In the next one, however, I could move this side here and this side here, and I would actually have these bits extra. So this one is going to have a longer perimeter than the original square. Same in this one, right? I could move this to the top, but I've got these bits extra, so it's not that one. The fourth shape here is like the first one, but we've done that twice. So this is the same as this is the same as this. These are the same and these are the same, so that will have the same perimeter as the original one. And the same here, it's just the corners pushed in the T, so that one will be the same as the original square. And the same here, I've got all 4 corners pushed in, but it's still the case that these are the same as these are the same as these are the same as these, and these are the same as these. So that one will have the same perimeter as well. So the answer here is that 4 of the shapes have the same perimeter. Christopher has made a building out of blocks. The grid on the right shows the number of blocks in each part of the building when viewed from above. Which of the following gives the view you see when you look at Christopher's building from the front? And we're told where the front is here. So to work this one out, I'm going to just go from left to right, thinking what will I see for each section. So in the left-hand one, I've got 1, 2, 3, 4. The 4 will be the highest one. That will be the one that ultimately determines what it's going to look like. And it's the same for all of the others. It's going to be the tallest one which is going to determine it, right? So the 3 here is the tallest. I won't see the 2 behind it. Okay, the 1 and the 2 will be in front of the 3, but I'll see something that's 3 units high. And same here, I'll have a 3 and a 2, and they will be the highest in each one, and that will be what I see. So I need something that's got 4, 3, 3, 2, and the correct answer here then is E. That's what it would look like from the front. In a class election, each of the 5 candidates got a different number of votes. There were 36 votes cast in total. The winner got 12 votes. The candidate in last place got 4 votes. How many votes did the candidate in second place get? Well, if we take off the 12 and the 4 from the 36, that's 16 in total. We've got 20 votes left to allocate to the other candidates. We know they've all got a different number of votes, and so the other 3 candidates must have somewhere between 5 and 11 votes. So let's just think about it. If the first place candidate had 12 votes and the second one had 11 votes, that would leave us 9 left for the other 2. So at least one of them would have to have 4 or fewer. So it can't be 11 for the next one. If it was 10, there'd be 10 votes left. Again, I'd have to have like 6 and 4 or 5 and 5, but that would both of those would mean a duplication, so it's not going to be 10. With 9, there would be 11 votes, so it could be 9, 6, 5. That would work, wouldn't it? And then if I tried 8, I suppose I would have 12 votes left, so I could have 8, 7, 5 as well. If it was 7 or less, it's not going to work, because now I'm down to 13, so I have to have either something bigger than 7 or another 7, so anything lower than that doesn't work. And the 2 options here are that the second place candidate could have either 9 or 8 votes, and so the answer here is C. And of course we don't know which of those it is, we just know that they are the only possibilities. The diagram shows a wooden cube of side 3 centimeters with a smaller cube of side 1 centimeters cut out of the corner. A second cube of side 6 centimeters has a cube of side 1 centimeter cut out at each corner. How many faces does the shape formed from the second cube have? So we can see in this first shape, we would initially have 6 faces, but with this corner cut out, I've got all of the original 6 faces, and I've got an extra 3 faces here. So this one would have 6 plus 3, which is 9 faces. In the cube that we're thinking about, this is going to have happened in all the different corners. Now it's a 1 centimeter cube cut out of a 3 centimeter length, so it's not going to meet the other cutout. It's going to be a separate cutout in this corner over here, and we know we've got 8 corners in total on the cube, so I'm actually going to add 3 extra faces 8 times from the original 6. So the answer here is 6 plus 3 times 8, or 6 plus 24, which is 30, and so the answer here is D. How many 2-digit positive integers have a difference of 50? Well, let's think about the smallest 2-digit integer to begin with. That would be 10. Well, if I added 50 to that, that would be 60. So 10 and 60 certainly work here. They're 2 positive integers that are both 2 digits and have a difference of 50. So if I keep going, I could do 11 and 61, I could do 12 and 62, and we don't want to keep writing all of these down. Let's just think about the last one that we're going to get here, which is going to be when this is 99, and so this one here will be 99 minus 50, which is 49. So it's really just a question of how many numbers are there between 10 and 49, or between 60 and 99. Let's do 10 and 49. To work out how many values there are, we do 49 minus 10 plus 1, and then that gives us that there are exactly 40, or you can count that up in whichever way you like, but either way the answer here is E, 40. A lot of goals were scored in a hockey match I watched recently. In the first half, 6 goals were scored and the away team was leading at half time. In the second half, the home team scored 3 goals and won the game. How many goals did the home team score altogether? Well, if we think about what might have been the score at the end of the first half, let's have the home and the away team. 6 goals were scored and the away team were leading. So it could have been 0-6, it could have been 1-5, it could have been 2-4, but that's it, right? 3-all, etc. won't be the away team winning. Now the home team scored 3 goals and won the game. So if the home team scored 3 goals in each of these scenarios, it would be 3-6, 4-5, or 5-4. This is the only one where they would be winning, and it must have been that the away team didn't score any goals. There's no situation where the away team here could score more goals in the second half. So we've got it's 5-4. So how many goals did the home team score altogether? The answer here is 5, which is C. In a certain month, the dates of 3 of the Sundays are prime. On what day does the 7th of the month fall? Now, This sounds like quite a difficult question, but there aren't as many options as you think here, right? Because if the two Sundays next to each other were prime, it would have to be either something like, the second and then the 9th, or the 3rd and then the 10th, right? One of them is going to be odd, one of them is going to be even. But the only even prime number here is 2, right? But if I take the second as one of the options, then the next one would be the 9th. Well, that's not prime. So actually, and then the next one would be the 16th. And so actually we can't make that work. I only get 2 prime Sundays at most here. So I have to start with an odd prime, and then it's going to have to be every other week that I get another prime number, because the 2nd and the 4th ones are going to be even, right? So it's 3rd, the 10th, the 17th, the 24th, and the 31st. And if I go anything beyond that, the last Sunday is going to be a date bigger than the 31st. So this is the only way that it can work. And luckily 3, 17 and 31 are all primes here. So these must be Sundays. And then the 7th of the month, well, if Sunday is the 3rd, the 4th is going to be a Monday then, the 5th is going to be a Tuesday, the 6th is going to be a Wednesday, and then the 7th finally is going to be a Thursday. And so the answer here is that the 7th must be a Thursday. Alicia wrote an integer in each square of a 4x4 grid. Integers and squares with a common edge differed by 1. She wrote a 3 at the top left corner as shown. She also wrote a 9 somewhere in the grid. How many different integers did she write? Well, if we go through and just write the largest possible numbers we can here, right, something next to the 3 is increased then to be a 4, and the things that are next to 4s I'm going to increase to be a 5, and then the ones next to a 5 I'm going to increase to be a 6, and so on. These will become 7s, these will become 8s, and I can only just manage to get a 9 in the bottom corner here. So this really must be the arrangement that she writes here, because I've really made the numbers as big as I possibly can, and I've only literally just got this one option where we can have a 9. So it must be that these are the numbers, and the options are 3, 4, 5, 6, 7, 8, and 9, and that is 7 different integers in total, and so the answer here is D7. Ali, Bev, and Chaz never tell the truth. Each of them owns exactly one coloured stone that is either red or green. Ali says, my stone is the same colour as Bev's. Bev says, my stone is the same colour as Chaz's. Chaz says, exactly 2 of us own red stones. Which of the following statements is true? Well, the way I like to do this is just to test out A, B, and C here. Let's say Ali, Bev, and Chaz. And let's suppose, to begin with, that we just pick at random and say, let's say Ali's stone is red. Right, well, Ali says, my stone is the same colour as Bev's. So that's false, because they all lie all the time. So Bev's must be a different colour from that, and so it must be green. Bev says my stone is the same colour as Chaz's, so actually Chaz's must be different from hers, so that would be red. And then Chaz says exactly 2 of us own red stones. Well, that would now be true, and so because Chaz is lying, this option can't be correct. So it must be then that, if we now try Ali has a green stone, for the same reasons, Bev's has to be different, and so it'll be red, and then Chaz's has to be different from the red one, which is green, and now it is false that exactly 2 of us own red stones. So this is the only way that this information can be consistent, and if we go through and look at the different options, the one that's correct here is that A, Ali's stone is green, and so that's the correct answer. There are 66 cats in my street. I don't like 21 of them because they catch mice. Of the rest, 32 have stripes and 27 have one black ear. The number of cats with both stripes and one black ear is as small as it could possibly be. How many cats have both stripes and one black ear? Well, a Venn diagram is a good way of representing this sort of data. I'm going to put all the cats that have stripes in this first circle, all the ones that have one black ear in the second one. That means anyone with both will be in the middle here, and I suppose anything with neither will be on the outside here. But first we've got to deal with this information about the ones that catch mice, and it's a bit of a distraction. We've got 66 cats in the street, 21 of them catch mice, so there's 66 minus 21, which is 45 left, that are going to be in our picture here. If you like, for the Venn diagram picture, we could put another section here with these 21. They're not really relevant to the rest of this question. So we've now got 32 that have stripes and 27 that have one black ear. Now if you add 32 plus 27, you get 59. Okay, so if there were no cats that had both stripes and one black ear, we could keep them all separate like this, 32 and 27, and that would be 59 in total. But we know there's only 45 in total, so some of them have to have both. The difference between 59 and 45 is 14, so it must be at least 14 that have both. So if I put the 14 in here, that means 14 of these 32 also have one black ear. So there's only 18 here that just have stripes, and of these 27, 14 also have stripes. So there's just 13 that have just one black ear, and that's as small as it could possibly be here. We've got none outside with neither here as well, and I could, if I increased the number 15 here, then I may also be able to have some on the outside with neither. But 14 is the smallest that number could possibly be, and so the answer here is E, 14. A group of 40 boys and 28 girls stand hand in hand in a circle facing inwards. Exactly 18 of the boys give their right hand to a girl. How many boys give their left hand to a girl? This is quite a tricky question, I think, and you can really go around in circles, no pun intended, with lots of different ways of doing this. But there is a fairly simple answer to it if you really, really focus down on it. So let's think about that. 18 of the boys give their right hand to a girl. So let's say there's 18 of the boys that are giving their right hand to a girl. That means that the rest of the boys, another 22, give their right hand to a boy. Okay. Now, these boys that have been given the right hand of another boy are the only ones who are giving their left hands to a boy, right? Because these are the only boys who are giving their right hand to another boy. These are the only boys who are giving their left hand to another boy then. So there must be exactly 22 of those. So that means that there's 18 boys who are giving their left hand to a girl. And that's the answer. How many boys give their left hand to a girl? 18. And so the answer is C. For how many three-digit numbers can you subtract 297 and obtain a second three-digit number, which is the original three-digit number reversed? A good way of thinking about this is to think of subtracting 297 as subtracting 300 and then adding on 3. Because for most numbers, let's say I'd started with 825, if I subtract 300, that takes 3 away from the first digit, and then I add on 3 again, that will add 3 to the last digit, right? So the first digit has gone down by 3, and the second digit has gone up by 3. And that's going to be true when you subtract 297 from most numbers. Now I say most numbers because if you started with something like 597, 598, 599, actually subtracting 297 here would give us 300. So the ones very close to the next 100 don't quite work. But for these ones, the middle number does change. So we don't need to consider those. We're not looking for those sorts of numbers. So what we are looking for is a number like 825, that one's worked here, right? 825 becomes 528, where the first digit is 3 larger than the final digit. So anything of the form 9x6 would work, for example, where x here can be any number from any digit from 0 to 9, so there would be 10 options here. I could also do anything 8x5, where again x is from 0 to 9. I could do 7x4, I could do 6x3, I could do 5x2, and I could do 4x1, and again there are going to be 10 of each of these types, and that takes us to the maximum possible answer here of 60. So even if you're a little bit uncertain at that point, if you found 60 of them, you know for this multiple choice question that must be the answer, but we've shown clearly why that's all of them as well. The diagram shows a square PQRS with area 120 centimeters squared. Point T is the midpoint of PQ, the ratio QU to UR is 2 to 1, the ratio RV to VS is 3 to 1, and the ratio SW to WP is 4 to 1. What's the area in centimeters squared of the quadrilateral TUVW, i.e. this bit in the middle here? Just made a big copy of the diagram here, and you've got a choice here. You're either going to have to work with some slightly awkward fractions, or you can scale the numbers up a bit and avoid the fractions, but maybe just have to do a little bit of multiplication with bigger numbers. I prefer avoiding fractions because I know I can use some multiplication tricks as we go along to simplify and speed up the calculations as well. So what I notice here is that we have a ratio of 1 to 1, of 2 to 1, of 3 to 1, and of 4 to 1. And so if I take the lowest common multiple of the number of parts in these ratios, so the lowest common multiple of 2, 3, 4 and 5 here, I'm going to get 60. So I'm just for now going to call the side length of the square 60x, and then I can fill in that these would be 30x and 30x, these would be 40x and 20x, because T is the midpoint, this one is the ratio 1 to 2, ratio of 1 to 3 on the top here, so that would be 15x and 45x, and on the left here I have got 48x and 12x. That's the ratio of 1 to 4. This might seem a bit complicated at first, but you see now what I can do is I can just work out the areas of all of these 4 triangles, subtract them from the total, and then use the result to get the answer to the question. So the area of this triangle A here, right, that's just going to be a half times 20x times 45x, and again I've just half times 20 is 10, so this is 450x. If I look at B here, that would be a half times 30x times 40x. So I've got a half of 40 is 20. 20 times 30 gives me 600x for that one. The area of C is a half times 48x times 15x. So I've got to do 24 times 15, which gives me 360x, right? 240 plus 120. And so for D, I've got a half times 12x times 30x. So again, 6x times 30x here is a 180x. And if I add all of those together, you can check that you get 1590x. And the overall area of the big square here is 60x times 60x, which is 3600x. So actually the quadrilateral that we're looking for, the inside one, is 3600x minus 1590x, which is equal to 2010x here. Okay, so now why have I done all of that? Well, it's because I want to know the area of this quadrilateral, and I now know that the fraction that I'm looking for is 2010x over 3600x. If you had a bit of foresight here, you might have known the x's were going to cancel, and you could have just forgotten about that from the beginning. So I now just need to work out that fraction of the total that we started with, which is 120 centimeters squared. And again, you see I can cancel rather than doing any awkward multiplications. I've definitely got a factor of 10 top and bottom here, so I can get rid of one of those zeros. And then 120 over 360 is just 1/3, so I actually just want 201 divided by 3. And finally, we can do a division of 201 divided by 3 and get 67, and that's the answer then. B, 67. They say you could do it with fractions instead, but I quite like that way. There's going to be some calculation either way here. Avoiding fractions, I think, always saves a little bit of mental strain. In the Maths Premier League, teams get 3 points for a win, 1 point for a draw, and no points for a loss. Last year, my team played 38 games and got 80 points. We won more than twice the number of games we drew, and more than 5 times the number of games we lost. How many games did we draw? Well, if I look at the closest multiple of 3 less than 80, that's 78, and 78 divided by 3 gives me exactly 26. So that's certainly an upper bound on the number of games that we've won. We can't have won any more games than that. So let's think about if we have won 26 games, then there would be 78 points from those wins. I would have to have another 2 points to get to 80 points in total, so there'd have to be 2 draws. 26 plus 2 is only 28 though. We've played 38 games, so there would be 10 losses. Now we need to have won more than twice the number of games we drew. That's certainly true here, but we also need to have won more than 5 times the number of games we've lost. Well, 26 isn't more than 5 times 10, so that can't be the answer. But all we've got to do now is just to keep searching. So if I had 25 wins, then I would have 5 draws, because I would have 3 fewer points from the wins. I would need to get 3 more points from the draws, and then that would just leave me with 8 games lost. That still doesn't satisfy the condition, because 25 isn't more than 5 times 8. If I keep searching though, 24 wins would correspond to 8 draws, another 3 points needed from the draws there, and then 6 losses. 24 is only 4 times 6 though, so these two still don't work. If I go down to 23 wins though, that would bring me to 11 draws and 4 losses, and now 23 is more than 5 times 4, and so that works. Now if I go any further, 22 wins and 30 would then give me 14 draws and 2 losses. Now 22 isn't more than double 14, so that doesn't work. This is the sweet spot where we have satisfied the condition, and so the number of games drawn here must be 11, and so the answer is D. For a given list of 3 numbers, the operation change sum replaces each number in the list with the sum of the other 2. For example, applying change sum to 3, 11 and 7 gives 18, 10 and 14. Arif starts with the list 22, 3 and applies the operation change sum 20, 23 times. What is the largest difference between 2 of the 3 numbers in his final list. So make sure you understand how this works. That's why they've given you an example, right? 3 plus 11 is 14, 3 plus 7 is 10, and 11 plus 7 is 18. So you can see how it works. And a good way to start here is just to start playing around with the numbers that we've been given. So if I start with 22 and 3, right, I do 2 plus 3, that gives me 5. I do 20 plus 3, that gives me 23. And 20 plus 2 gives me 22. Now, the largest difference between two of the three numbers initially was 20 minus 2, which is 18. And it's still 18. It's 23 minus 5. Let's just do this once more. So if I add 23 and 22, I get 45. 5 plus 22 is 27, and 5 plus 23 is 28, and the largest difference, 45 minus 27, is still 18. So that's quite a good indication that the answer here might be 18, and that this largest difference perhaps doesn't change. Now we can't check that by doing it 23 times. If you were short of time in a maths challenge, at this point you might just go for the answer and think about checking it later. We can be a bit more rigorous here though. So let's suppose we start with three numbers x, y, and z, and let's just say that they're in order. It doesn't actually matter what order the numbers are written in here, right? You always work out the sum of all of the pairs, so I can just rewrite them in this order, and it's not going to make any difference. So the numbers that I get here are y plus z, x plus z, and x plus y, right? Adding the other pairs together. And I can also put these in order, right, because x and y are the smallest numbers, so it must be that x plus y is smaller than x plus z, because z is bigger than y, and also x plus z is less than y plus z, because y is bigger than x. So the largest one minus the smallest one here is z plus y minus x plus y. We can see that the y's cancel out here. I've got a y and a minus y, and I'm just left with z minus x, and that is the same as the difference between the largest and the smallest numbers that I started with. So this change sum operation really can't change this value of the maximum number minus the minimum number, so we can be really confident that the answer here is B18. Emily makes 4 identical numbered cubes using the net shown. She then glues them together so that only faces with the same number on are glued together to form the 2 by 2 by 1 block shown. What's the largest possible total of all the numbers on the faces of the block that Emily could achieve? Well, so we're trying to maximize the numbers that we can see here, and so that's the same as trying to minimize the ones that will be glued together. And if you think about the corners that are glued together, they have to be two that are next to each other, two that share an edge. So if I'm trying to get the minimum there, well, I'd really like it, if possible, to be 1 and 2 on those inside faces. But 1 and 2 on the net are opposite each other. They, you know, if I had the 1 on this side, the 2 would have to be on the opposite side. So we can't do 1 and 2. The next best we can do is 1 and 3, and actually 1 and 3 folded together would share an edge here. So what we're going to do is we're going to make the inside numbers all 1s and 3s, and then the numbers left on the outside will be 2, 4, 5 and 6, and I'm going to have 4 cubes in total that I can see. So in total I'll be able to see 4 lots of 2 plus 4 plus 5 plus 6. That is 4 lots of 17, and 4 times 17 is 68, and so the answer here is C, 68. Tony had a large number of 1p, 5p, 10p and 20p coins in a bag. He removed some of the coins. The mean value of the coins removed was 13p. He noticed that a 1p piece in his group of removed coins was damaged, so he threw it away. The mean value of the rest of his removed coins was then 14p. How many 10p coins did he remove from the bag? Problems to do with averages are often best solved thinking about the total amount. So let's say that he had n coins that he removed to begin with, then the total value of those coins would be 13np, because their average value was 13, right? The average is the total over the number of coins, so the total is the average times the number of coins. Now he's going to remove a single 1p piece, and then that'll be worth 13n minus 1p, and at this point the average is 14. But now there's n minus 1 coins in the bag with an average of 14p, so that would be 14 times n minus 1 would be the total. So this total, 13 n minus 1, must be 14 lots of n minus 1, and so I can just solve this equation. 13n minus 1 equals 14n minus 14, and then if I subtract 13n from each side and add 14 to each side, we get n equals 13, and so it must be that there are exactly 13 coins that he removed from the bag. Now these 13 coins have a total value of 13 times 13p, because 13p is the average value of the coin, so 13 times 13 is 169p. So the question is, how can we make 169p from 13 of these coins? You could do this in a couple of different ways. You might start by just trying as many 20p's as possible, for example, and then sort of searching through, right? Because I could say 8 times 20p takes me to 160p, and then I've got to try and make up the 9p from the other coin. So I won't use any 10s here, but I could use a 5, and then I could do 4 1s. And actually that does give me an answer that needs exactly 13 coins. And so actually, because this is a challenge question, there's no more information needed. Once I've stumbled upon that answer, I can know that the answer here does have to be A. But you might want to double check that there are no other possibilities. You could now start by searching through, thinking about 7 lots of 20p, 6 lots of 20p, until you get far enough that you're confident that there's no way of doing it. Or you can think that to get to a total of 169p, you are going to need to use either 4 1p coins or 9 1p coins, and that narrows it down as well. I'm not going to go through all the options here, but you will find as you go through all of those that nothing else is possible apart from this combination, and so that really is the answer. And don't forget, you can find loads more questions like this with hints and solutions over at the Mathsaurus Courses website for the Junior Kangaroo, for the Olympiad, for all of the other maths challenges, from the first maths challenge right up to the senior maths challenge. Or if you want to watch more solutions like this on YouTube, check out this video on the screen right now.